is formulate a whole bunch of problems as math programs. So it's just going to be exercise, and so most of today's lecture will be, taking up a problem statement and converting it into a linear programming problem, just writing it down, the linear program. So we'll probably do about 7 or 8 different examples, and once we understand how to actually do this, we'll worry about finding ways of actually solving these linear programs, which we'll start from the next lecture. Okay? Now, before I tell you what the problems are, I also want to tell you about the TA for the course and office hours, so we'll finalize all of that before we begin the lecture. Okay. So we do have a TA now. It's Sturgios his office is in I think it's 325 Mud maybe, or 335, I'm not sure. It's right opposite, so it's the last office along the corridor. Okay? It's diagonally opposite to my office. So he's going to be the TA for the course, and so his responsibilities include helping you with your homework, helping you with whatever questions you may have about the material that you're learning. He will be available for at least a couple of hours a week to do this for you. Now, he said Tuesday afternoon, 4 to 6 would be good for him. Is that, do you have a class? Which course is it? Okay, so there's an advanced engineering and corporate economics. I heard probability from somewhere. Okay. How about, so I assume Thursday same time would be bad as well. Okay. How about Wednesday mornings? Let's say Wednesday 10 to 12. How many of you have a conflict? Is it for the entire 2 hours or?
11.
Simulation from 11. Okay, so you still have 10 to 11. Okay, so let's agree on Wednesday 10 to 12. So that's 10 a.m. to 12 noon. This is tentative, so I want to check with him as well before confirming. Okay. Then I also would like to hold office hours, so this is office hours. So since he's holding Wednesday office hours, I can probably hold mine Thursdays. Now Thursday soon after class, 11 to 1, let's say. Is that good for people? Okay. Okay. Now, because his office hours are on on Wednesdays, mine will be Thursdays. So I'm going to make the homework for the course due. Yes. On Thursdays, exactly. 11 to 1. 11 to 12:30. So shall I move it to 12 noon to 2 p.m.? We can have lunch. I could say 10:30 to. Okay, so you have it 11 to 12:30, right? Well, so how many of you are taking the production management course? I mean, there should be a sizable number. So why don't we do the following? So let's have it as 11 to 1 with the understanding that I'll be happy to see you beyond this time if you show up. Okay. So in other words, if you come at 12:45, I'll be happy to spend whatever time is necessary. Okay. And always, in addition to these, you can always see me by appointment. If you just email me, give me a day or so, we'll be able to meet at some convenient time. Okay. So if this doesn't work too well, we'll always change it. But for now, let's actually stick with the schedule. Okay. So because of this, I'd like to make homeworks due Fridays. Now, how many of you actually come to the university on Fridays? I know some of you work, a lot of you work. So I'm going to make it due Friday, sometime, Friday noon, let's say. But you're perfectly welcome to turn in your homeworks ahead of time. So if you're not going to be around Fridays, you can drop it off Thursdays in my office. Okay. So homeworks. So the best way to turn in homeworks would be to leave them in my mailbox, which is in the lounge in the department. You can give it to me soon after class if you have it ready. You can also hand it in to the TA. Okay. Any questions? Yes.
I checked the library. Our textbook, there's only one copy in the reserve, but they get borrowed by somebody a long time ago, never returned. So there's no book on reserve in the library.
Okay, so I will. Library copy. So we'll make sure that there's another copy in the library somehow. Just give me a few days and we'll arrange that. Anything else? Okay. So far, we still have not moved the course web page to coursework, although I posted homework 1 there as well, and I sent you all an email. So if you didn't receive any email at all from me about the course, please come and see me after the lectures. Okay? And after a week or so, we'll probably shift everything to coursework. Okay. So with that long prelude, let's actually get started with some interesting stuff. Okay? As I said, what I'd like to do today is discuss various kinds of formulations of linear programming problems. And what most people would tell you is that formulating a problem as a math program is an art. I mean, it's something for which you cannot always follow a fixed recipe and get the answer. But at the same time, it's useful to actually study various classes of models that people have been successful in formulating. And once you do that and you see a new problem, you'll recognize that certain components resemble certain components of a model that you know. And so by pattern matching, you typically can formulate a large part of the problem, if not the entire problem itself. So the reason for our studying some of these categories of problems is mainly to understand what kinds of problems do come up in real life. And the actual problems that you may face would have features of various components of these problems. Okay? So the first, we've already done one of these, which is the machine scheduling problem, where we took a statement and wrote down something in mathematical terms. So let's do a few more. Okay? So here's one. So these are what are called blending models. And so they often have the following structure. Okay, so let's say that there are 4 different kinds of gasoline. Okay. And each kind of gasoline is distinguished by a pair of indices. So if I tell you the values of these two, now if I give you the values of these two indices, that specifies a particular type. Okay, so specify the type. So for instance, you could have 99 and 210. So that's a certain kind of gasoline. You could have 70 and 335. You could have 78 and 280. You could have 91 and 265. Okay. So these are the 4 different kinds of gasoline. So you can think of this as some kind of a quality rating, and this as a different kind of a quality rating. Okay, so the details are not important. And the point is that you can use these to manufacture other kinds. So for instance, so let's say that the cost of a barrel of this type of gasoline is $48. Okay. Similarly, the cost of this is 43. The cost of this is 58, and the cost of this is 46. So we have available these 4 kinds, and we want to make something out of these. So in other words, you're going to take some amount of this, some amount of this, and blend them to get something whose indices are somewhere in between these 2 things. Okay? So the goal is to produce, so find a minimum cost blend X, Y, let's see, such that X is between 85 and 90, and Y is between 270 and 280. Okay. And so the tacit assumption in all of this is that if you take a barrel of this and a barrel of this and put them together, you get 2 barrels of a hybrid type, where the first index is the average of these 2 numbers, and the second index is the average of these 2 numbers. Okay? In other words, when you combine these products in proportion to the amount, the index will be weighted. Okay? So if you combine equal parts of these 2 things, you'll get just a simple average of these 2 numbers. If you take 2 units of this and a unit of this, you will get 2/3 of this contribution and 1/3 of this, and so on. So is that clear? So this is how most blending problems are formulated. Okay. So you would like to get some product whose first quality index is between 85 and 90, second index is between 270 and 280, and there may be many, many ways of achieving such a hybrid product. And among all possible ways, you want to find one way that achieves the minimum cost. Okay? Now notice that I said you want to find one way to achieve the minimum cost. Okay, so there may be typically many ways of achieving the minimum cost, but there is always a single minimum cost. Okay? So you may have two different ways of getting a blend that achieve the lowest possible cost, but yet are different. Okay? So it's quite common in linear programming problems to have multiple optimal solutions. So there are many ways of achieving the best possible profit. However, the best possible profit itself is a unique number, okay, if it exists. Okay? So that's not too hard to see. So how would you formulate this problem as a linear programming problem? Yes.
We want to minimize, if we say we take A of 1, B of the second, we want to minimize 48A plus 58B plus 43C plus 46B under the two constraints that 99A plus 78B plus 70C plus 91D over A plus B plus C plus D.
Okay, very good. So let me stop you there and say the following, that of course you're right, and I just want to expand on some of the things you said. The first thing to do when formulating is identifying what your decision variables are. What is it that you want to determine? Or what constitutes a solution to the problem? So in this case, what constitutes a solution? Of course, there's the final outcome itself, which is the value of x and y. But really, what you want to do, what you want to know is how many parts of this should I mix with how many parts of this, how many of this, and how many of this. Okay? And that you call A, B, C, and D. Okay? So let A, B, C, D be. So I'm just going to use the number of parts of, 1, 2, 3, 4, respectively. So, I'm being very, very sloppy in my writing, but you know what I mean. So I'm going to take A units of this, B units of this, B units of this, and B units of this. Okay? Yes? Thank you. Okay. So I'm going to use A, B, C, D to denote the respective numbers. In fact, I'm going to do actually, let's then denote the fraction. Well, let's actually just work with this. Okay. So we'll see in a little bit what I mean. Okay. So if I use A parts of this and B of this, C of this, and D of this, I'm going to end up paying 48A plus 43B plus 58C plus 46D, right? That's going to be my cost. Okay. And how many units of gasoline am I getting out of this? So it depends on, okay, so if you want to get 1 unit, okay, so let's say that this, and we say that we get 1 unit of gasoline. Okay. So this is going to be my cost, assuming we get 1 unit of gasoline. Okay? So let's make that assumption that after we do this, we get 1 unit of gasoline, and this is going to be the cost, and I want to minimize this. Okay? So minimize this quantity. Now, of course, if all I had to do was minimize that quantity, I could set A to be negative infinity, and I would minimize that quantity, right? So for this to be meaningful, you need to formulate the relations between A, B, C, and D that need to hold, so that what you're doing constitutes a valid solution to the problem. Okay? And that's where the constraints come in. So the A, B, C, D are the decision variables. This is the objective function, and you want to pick values for the decision variables subject to satisfying certain constraints, which are relationships involving the decision variables. Now, what are those constraints? Okay, so the first constraint is that you want to get 1 unit of gasoline out of this, okay, which is, so A plus B plus C plus D is just 1. Okay. Not only that, A, B, C, D are all non-negative. Okay. So this really suggests that what you're doing is the following, that A, B, C, and D represent the fraction of types 1, 2, 3, and 4 of the gasoline that you're going to use to end up. Okay? So in other words, if you imagine this hybrid product that you want, okay, imagine that that exists. Given that that exists, A, B, C, and D would represent the fraction of types 1, 2, 3, and 4 that you put in to formulate that hybrid product. Okay, so that's what it really means. Okay, then what other constraints do you need for this to satisfy? Yes?
70B plus 78C plus 91D plus 73
Okay, so 99A plus 70B plus 78C plus 91D has to be between 85 and 90, and I won't bother writing down the other constraint. Okay? So the second constraint is exactly like this with different set of numbers, and that would be a formulation of the blending linear program that you started with, of the blending problem that you started with. So there are many, so these kinds of the blending constraints would come up in several other problems, okay, some of which we may study in the future, but this is just one class of linear programs. And historically, these are among the earliest linear programs that were formulated, mostly for problems in the chemical industry. Okay. Any questions about this? In many ways, this is just as easy or difficult as the problem that we already formulated. So it's just a warm-up exercise. Okay. Let's do another problem. So let me get rid of this. So this is a staffing problem, and it has the following rules. So each person works 5 consecutive days and takes 2 days off. Okay. Yes. Uh-huh. So, okay, so in the previous problem, your x is going to be this, okay? I mean, I shouldn't have used x. Whatever blend is, its first quality index should be between 85 and 90. So that constraint is written down as this. Okay. There's going to be another constraint that looks exactly like this with 270 and 280 on either side. I just didn't write it yet. Okay. So in a staffing problem, typically you want, so most problems of this flavor have the following features, that you have a certain requirement. Okay, let's say you're running a hospital, you need to have so many nurses each day to make sure that all the patients are cared for. Okay? And the number may be different for different days, which may have to do with, the number of patients that have historically required care during each of those days. Or maybe you have a good forecasting software that says, over the next week, this is going to be my requirements for nurses. Okay? Now, of course, if you didn't have to deal with people, you could say, every day I'm going to employ these many, and on Tuesday I have 45 people, on Wednesday I want only 5, on Thursday I can, hire 30 more, and so on. But typically, you have somebody working for you, and you have to respect their constraints, their feelings perhaps as well. And normally, as we all do, people work 5 consecutive days, and they have 2 days off. So if somebody starts on a Tuesday, you cannot ask that person to not come Wednesday, but come Thursday, Friday, and take Saturday off, and so on. So typically, you have a constraint that looks like this. Okay? So the question is, suppose you have this constraint, and suppose your demands are, D1, D2, D3. Okay. So let's say that this is the staff requirement over a week, and every week it stays the same. Okay? So on Mondays you always need D1 people, on Tuesdays you always need D2 people, and so on. And anybody who starts on a Monday works Monday through Friday. So somebody who starts on a Tuesday works Tuesday through Saturday, and so on. So the question is, how would you find a feasible staffing schedule that involves hiring the fewest number of people? So you want to minimize the total number of people working for you. So find a staffing schedule that minimizes the total number of people. Okay. So of course you could always have, if you could always have more than D1 people on Monday. That's just a lower bound on the number of people you need. So once again, when you're asked to formulate a problem as a math program, you want to identify decision variables, you want to identify the objective function and the constraints in terms of the decision variables. Okay? So what's a natural choice for a decision variable? Yes?
We can have 7 variables indicating how many workers work in that particular first day.
Okay.
And formulate probably 7 equations.
Okay, so let's actually do that. So it's clear that we need 7 variables. Okay. And so the suggestion was, so you could say x1 is the number of people who work on day 1. Okay. And in general, xi is going to be the number of people who work on day I, right? So this we can. So instead of writing 7, you can just write. So this is this is just notation. It's just a short form saying that you have 7 of these. Okay. So these are your decision variables, and then what happens? What's your objective function? What are the constraints? So the constraints are easy, right? You just need to satisfy the daily demand. Okay? So you want to make sure that xi is greater than or equal to di for I equals 1 through 7. Okay? And you, of course, you want to make sure that xi's are non-negative, but presumably the di's are all non-negative, and so that's already taken care of. But we can add it in anyway. Yes?
For this problem, though, are we going to consider rollovers from the previous week so that if somebody on D starts B7, we're going to count them B1, B2, B3, and 6?
Yes. So think of these as days of the week. So somebody who starts on a Sunday works Sunday through Thursday, I guess. Okay. So the constraints are easy, that you want to have enough people to satisfy the appropriate demand. Now, what is your goal? Your goal is to minimize the total number of people that you hire. Yes?
Minimize situation equals 1/7 of xi.
Okay, so you want to minimize summation xi. Okay, so over 5. So let me actually write this down separately. So that's one objective. Okay. So here's another objective: minimize summation xi over 5. Okay. Any other suggestions? So let's actually understand a couple of things about the 2 linear programs that we've written down. These are 2 different linear programs because they seem to have different objectives. Okay? And then come back to this problem itself. So first of all, this and this look different. Okay? But as linear programs, they will have the same they don't have the same objective value, of course, but there's a clear correspondence between solutions of this LP and solutions of this LP. So if I find an optimal solution to this problem, okay, the same solution is optimal for this objective function as well. It's just that you're changing the units by which you're measuring things. Okay. So these 2, as linear programs, have the same optimal solutions, and their optimal values are related by this factor of 5 business. Okay? So these 2 are not that different. So we may as well just work with this. And let me make another comment about this. So does anyone know what the optimal solution to this linear program is? Okay, very good. So if you want to solve this linear program, let's actually examine this LP and conclude that its objective value is exactly the summation of all the demands. Okay. Now notice that every x1 has to be at least d1. Why would you ever want to set x1 to be beyond d1? Okay. I mean, if d1 is 10, this constraint says x1 has to be at least 10. I could set x1 to be 10, okay, and that doesn't affect anything, right? These variables don't interact in any way. So setting xi equals di is an optimal solution to this linear program. Okay? Notice that I have not claimed that this is the right formulation of the problem that we started. Okay? I'm just saying that for this linear program, xi equals di is an optimal solution. Okay, and of course, if you add up all of these constraints, you get a new constraint that says summation of all xi is bigger than summation of all the di's. And here you have a solution such that the summation of all the xi's is exactly equal to the summation of all the di's. Therefore, this has to be optimal. Okay. Anyway, so I'm not going to belabor this because this is sort of an obvious point, that for this linear program, you would just set xi equals di, and that's an optimal solution. And you can convince yourself that that's indeed the case. Okay. Yes?
So we have to enumerate the constraints that people have to work to specifically to
Right.
So that's what
This, okay, so a couple of good points that are made. So first of all, what does this say? For this particular linear programming problem, this is an optimal solution. Okay? Now, for the starting problem that you started with, okay, what this is really saying is the following. If somehow you can find a solution in which exactly di people work on day I, then that is an optimal solution. But of course, this is not the total number of people you hire. Okay? The total number of people you hire, because of these constraints, you have no idea because you have not kept track of the right decision variables. Okay? So let me say that again. If for this problem, okay, I just tell you that 40 people work on day 1, 70 work on day 2, and so on, you need to work to figure out how many people actually started on day 1. In other words, you don't know how many distinct people there are, because some of them who come on Monday show up for work Tuesday, and some of them don't, and you have no idea who's who. Okay? So even though you have decision variables that seem to be the right thing, right, that you want to keep track of the number of people who work every day, it loses information that you need to formulate your problem, which is among these xi people who show up on day I, you don't know how many will come the following day, you don't know how many will come for the next 2 days, for the next 3 days, and so on. And so this is not an adequate set of decision variables. Okay? So I know exactly what you meant. So I deliberately misinterpreted what you said so that I could illustrate this. Okay? I know you were careful in saying the number of people who start work on day I. Okay? Okay. So instead, suppose you say that x1 is the number of people who actually start work on day 1. Okay? And similarly, xi is the number of people who start work on day I. Then, of course, any person starts work someday, And so, you cannot, so this is the right objective function. Okay? Because you look at anybody you hire, he has a shift starting on a particular day, and then he'll show up for work for the next 5 days. Okay? So that's the right objective function, but the constraints are now going to be different. So who will come to work on day 1? Well, all the people who start on day 1 will be there, plus the people who started on day 7, day 1 would be their second day. People who started on day 6, day 1 would be their third day. So anybody who starts his or her shift on days 4, 5, 6, 7, or 1 would come to work on day 1. And you want this quantity to be at least D1. Okay? And similarly, you want x2 plus x1 plus x7 plus x6 plus x5 to be at least D2, and so on. So again, you have 7 constraints capturing the demand for each day separately. Okay? So with the new set of decision variables, we have the right objective function, whereas with the old set, we couldn't formulate the objective function. But the constraints look a little more complicated than what we had before. Okay? But this is the right formulation of the problem. So any questions about this? So, the lesson and the summary that was almost killed off is that you need the right set of decision variables. Okay? That if you make a wrong choice of decision variables, you may not be able to capture what you really need. Okay? And one useful way to think about what the right set of decision variables is to ask yourself the following. What information constitutes a solution to your problem that you can actually verify? If you think about it in these terms, you will come up with the right definition. Okay? So here, if I only told you the number of people who show up for work on a particular day, that's not enough information for you to figure out how many people you've hired. Whereas if instead I tell you how many start on each of the days, that gives you enough information about how many were hired and how many would come to work on any given day. So if we get a chance, we'll see later that these are linear programs that have a special structure. So they have what are called consecutive one property. And so it so happens that linear programs of this sort can be solved efficiently, much more efficiently than general linear programs. And secondly, we are dealing with staff members, and you want an integer solution to the problem, right? You don't want somebody to be split in half. Of course, if it is staffing, you could do it without splitting the person, but you don't want such a solution. So, of course, if your demand is 47.5, then it's unreasonable to expect a solution not to have fractional values. But it turns out that as long as all data for this problem is integer, the optimal linear programming solution would also have integer values. So these are special classes of integer programs that can be solved as linear programs. And even as linear programs, they can be solved much more efficiently than general linear programs. And when we deal with network problems, we may touch upon this issue. Okay? But for now, it's just important to understand how we formulated this and what mistake I made originally in writing down a formulation of the problem. Okay? Any questions about this? Okay. How many of you have actually seen such a thing before? Okay. So let's do let's actually do one more relatively simple formulation. Okay. So I want to tell you that lots of problems that we formulate as linear programs are really integer programming problems. Okay? So of course there are some genuinely linear programming problems. Most of them are really integer programming problems for which we ignore the integer restrictions. Okay? So here is another problem that's sort of interesting. And it'll teach us something. So you have, you observe, let's say, a certain relationship. So, X is the amount of advertising you do, and Y is the sales that you observe, okay, all in units of, $1 million, let's say. So when you invest 2 units in advertising, you get 1 unit in sales. When you invest 3 in advertising, you get 3 in sales, and so on. And of course, you don't want to keep experimenting with trying different amounts of advertising and observing how many units you end up selling. So you've done some experimentation and you somehow believe that there's some kind of a structure. There's some relationship between X and Y that looks like the following. So Y is going to be some A plus BX. Okay. And your goal, of course, is to find A and B. Find. Sorry? Thank you. Today is not a good day. I think I should just go home. Find A and B. Good. So you want to find values of A and B that somehow capture the relationship that you observe. Okay? Yes?
More like a regression.
Okay. So this is more like a regression problem. It's actually exactly the regression problem. Okay. Why are we doing this? So I don't want to show you how to solve the regression problem. I want you to see how you would write down a regression problem as a math programming problem. Okay. So the goal is, of course, to find values of A and B that somehow explain what you've observed. It's exactly what you do in regression. Okay. But what do I mean by good? What is your measure of goodness? Okay, so you have to tell me how you evaluate. So in other words, this is the actual relationship. If you fix any particular value of A and B, you will get some, for these values of X, your relationship might tell you different values of Y. So in other words, this, let's say Y bar, this is just going to be A plus 2B, this is A plus 3B, this is A plus 5B, and this is A plus 7B. Okay. So for any fixed values of A and B, I'm going to get another vector of numbers for my Y. And if somehow magically I get 1, 3, 3, and 5, then that's, you can't beat that, right? But of course, you're not going to be able to get 1, 3, 3, 5. So for instance, this is A plus 3B, and this is A plus 5B. So for both of these to be the same, B has to be 0. Okay? But if B is 0, then A has to be 3, and you get something different here. So it's clear that you're not going to match every entry. So the goal in regression, and you've seen this all, is that you want to find something that's not an exact match, but something that's fairly close. Okay? And that's a reasonable goal, because typically what you observe also has some error. And there's no point in expending a lot of energy trying to find the exact relationship between because what you're measuring is flawed anyway. So one common measure is to say that you want to minimize the sum of deviations. Okay? So you want to minimize y bar I minus yi in general. So we have 4 entries, okay, where one of these stands for these numbers and the other stands for this number. So you want to find A and B such that this quantity is minimized. Okay? That absolute sum of deviations is minimized. Okay? Is the problem clear to everybody? So what are the decision variables? What's the objective function? And what are the constraints? So, I have to say that I ask lots of easy questions. So don't be embarrassed to answer those. Please indulge me. Okay. Yes. Uh-huh.
Why are we looking at the deviation? We want to find the deviation between y bar and what items you were talking about, but in the original problem, you're talking about the difference between the advertising, how much input you're putting into advertising, and then what you're getting out of the sale. So why are we not looking at this?
No. So what I was talking about was understanding the relationship between advertising and sales. So it's not as though I want to match these two things. I want to understand the relationship between x and y, so that if I want to know if for x equals 100, I want to know what y I can expect without actually investing in $100 million of advertising. So I do what I can, and then I have something that suggests that the relationship might be something like this, and I want to figure out values for these that best explain what I actually observe, so that for things that I cannot observe, I have a reasonable prediction of what I might see. Okay. Yes, you had your hand up.
I feel like, should I tell you to change your objective function?
Let's actually stick with the objective function. Okay. So in other words, well, you could ask me to change the way I've written it, but what I want to do is the following. I want to compute the difference between 1 and this quantity. Okay. And if that's negative, I want to just negate that and add.
Saying, like, we're pretty much absolute value side of this mystical y bar thing or whatever.
Okay, so
we haven't really said what y bar is.
So let me actually rewrite that. So let's actually forget about this. Okay. So find A and B such that this quantity, A plus 2B minus 1 plus A plus 3B minus 3 plus a plus 5b minus 3, a 7b minus 5 is minimized. Okay. Does that make you happier?
Well, I mean, I was just going to say, minimize the, summation of y minus a minus bx squared, but whatever.
Okay. So that's just, so it depends on how you measure deviations, right? So when you use the squared objective, so this objective just says if you're deviating by 5 versus deviating by 1, deviating by 5 is just 5 times worse than deviating by 1. Your objective, which is more commonly used, just says that deviating by 5 is really, really bad compared to deviating by 1, because it's 25 times worse than deviating by 1. Okay? But it's just different ways of measuring or penalizing deviations. Yes?
Just looking for the absolute error.
Mm-hmm.
So the minimum, when the value is minimum, the variable is the median of the whole series.
Okay, so I'm not interested in solving the problem. Okay, so all I want to do is just write down this problem as a linear program. Okay, so for that, what do I have to do? First, I want to know what the decision variables are. Then I want to know what the constraints are and what the objective function is, both of these in terms of the decision variables. Okay. And then I want to check that what I've written down is a linear program. Okay. So let's actually do these in order, and they're all easy. Okay. So what are the decision variables for this problem? Just A and B, right? So decision variables are A and B. What are the constraints? Okay, so there are no constraints. And what's the object? Yes.
If it's fairly obvious that there's a positive correlation between x and y, can we say that b is greater than 0, or is that just some requirement?
Okay, so if you observe that there's a positive correlation, can you say that b is greater than 0? The answer is that you could say it, but you don't have to. Okay, so any reasonable objective function that in that case would have to explain that positive correlation, and your optimal solution would end up setting b to be positive. So one of the nice things about formulating problems is that you don't have to worry about how to solve the problem. So there's a clear separation between, you have a problem, you formulate it, and then let a piece of software deal with it. Okay? Now, of course, there will be instances where to get a good formulation, you will have to use precisely the sort of intuition that you demonstrated. So you may want to observe that there are certain features of the problem that will make certain values for the decision variables necessary, and you may as well add it as a constraint, because that may speed up the solution process, but you don't have to do it. Okay? So there are no constraints. These are the decision variables, no constraints. You could set A and B to be anything you like, and the objective function is just this. Okay? So everything is fine, except that there's one small problem, that this is a nonlinear function. Okay? So what does nonlinear mean? That typically, let's say, if I double, if I take, I take a certain term, and if my A and B are scales, that term has to scale, but that doesn't happen here. Another way to see it is that if I graph this function, the absolute value of x, I get a picture that I think looks something like this. And you can see that this is not a straight line. It's fairly close. It's two straight lines, but it's not one straight line, which is what you need for a linear function. Okay? So therefore, this is not a linear program. That's the only problem with this formulation. But can you make this into a linear program? And there's a little trick that people use to convert simple nonlinear programming problems into linear programming problems. And that's worth learning. Okay. So what I could do is to call this, I could just call this Z1. And I'm just going to call this Z2 and Z3 for this and Z4 for this. Okay. Now, of course, just because you call it something doesn't mean the problem doesn't exist, right? But if you call it that, you could write down your objective function as minimize Z1 plus Z2 plus Z3 plus Z4. Now, that is a linear function in the Z's. And now your decision variables are Z1, Z2, Z3, Z4, in addition to A and B. Okay? Yes.
Use this notation, then you can get the values of Z1, Z3, and Z4, the same possible to obtain with A and B.
Okay, very good. So that's a very good observation. As I said, just because I call it something else doesn't mean the problem doesn't exist, right? The problem still exists, and we have to do something about it. And right now, you may get, if this is your problem, and there's no interaction between the Z's and A and B, I could just set Z1 to be negative infinity. There's nothing stopping me from doing that, right? So of course, for this to be in any meaningful way related to the problem that you started with, there has to be something involving the Z's and A and B. So specifically, I have to say that Z1 equals A plus 2B minus 1. Okay? Z2 equals this, and so on. Okay? Is that clear to people? So now, of course, you have a linear objective function, but you have nonlinear constraints, okay, which is still not a linear programming problem, because a linear programming problem has to have a linear objective function and linear constraints. Okay? But notice the following. So I want to minimize this quantity, and I want Z1 to equal this. Okay? Now, what does that mean? So this is really saying Z1 has to be bigger than A plus 2B minus 1. Okay. Z1 has to be bigger than negative of that quantity. So, I mean, suppose this quantity, you have A and B such that this quantity is minus 3. Okay. Then these two constraints say that Z1 is at least minus 3. This is going to say Z1 is at least 3. Okay. And so Z1 will have to be at least 3. If this is a positive number, then Z1 will be at least that positive number, and Z1 will be at least the negative of that positive number. So this constraint won't matter, but this one will make sure that Z1 is at least that quantity. So collectively, these two would ensure that Z1 is at least the absolute value. Okay? So that's actually not related to this. If I have these two constraints, then I definitely have Z1 bigger than this quantity. If Z1 is bigger than this and bigger than this, then Z1 is at least the absolute value of this. y smaller than. Okay, so let's think of, so I want z is at least the absolute value of this. Okay. So what does that mean? You want z to be at least 5. So what I've written here is just saying z is at least minus 5 and z is at least minus of minus 5.
So it would be bigger before minus 5, it can be minus 4, it can be minus 3.
Yes, but this is going to be 5, right? So if z has to be bigger than negative 5 and bigger than 5, well, it has to be bigger than 5. Okay, so negative 4 is not allowed because it's going to violate this second constraint. We have both of these constraints. So let's again go back to this. If I have a number bigger than a certain quantity and a number bigger than the negative of that quantity, then that number has to be bigger than the absolute value of that quantity, okay? And vice versa. Okay? So if my constraint were this, then I could replace it by a pair of constraints that look like this. Okay? And I get rid of this nonlinearity. That's the key. That I can write a nonlinear constraint by a pair of linear constraints in this simple case. Okay? So if I had a constraint like this, I could always replace it by a pair of these linear constraints. Is everyone comfortable with that? Now, let's go back to the original problem. There, we don't have a bigger than equal to, we have an equality constraint. Okay? But what happens if I replace this by this constraint? Just, think about fixing the values of a and b. If you fix the values of a and b, then this says z1 will be equal to this quantity. This says z1 has to be at least that quantity. But you're minimizing z1. And z1 does not affect anything else. So why would you ever want to have something that's bigger than this? So in other words, if I solve this problem with greater than equal to constraints instead of the equality constraints, if I look at any optimal solution, each of those will be satisfied as an equality. It's exactly like in the wrong formulation of the staffing problem, we made an observation that if xi has to be bigger than equal to di, you're minimizing the sum of all the xi's, each xi will be set equal to the di. If you think back to that, that's exactly the same principle. That if you want to minimize z1, z2, z3, z4, the sum, and you have a constraint that says z1 is at least this, z2 is at least this, and so on, in an optimal solution, z1 would be set exactly equal to this, z2 would be set exactly equal to this. Okay. So as linear programs, this linear program is actually the same as this linear program. So where the equality constraints are replaced by greater than equal to constraints. So these two linear programs don't have the same feasible solutions, but they have the same optimal solution. And it's because we care only about optimal solutions, we may as well pretend that we have this linear programming problem and not that. And if you have this linear programming problem, you could take this constraint and replace it with a pair of linear constraints. Okay? So this is an example of a non-linear programming problem that can be linearized. It can be rewritten as a linear programming problem using a simple trick. Okay? So I'm going to let you process this at your own pace, and then we'll pick up things in the next lecture where I'll just start with a 5-minute overview of this technique. in another example. Are there any questions before we leave? Okay, so for those of you who came in late, so we fixed the office hours of the TA and me, and I'll update the web page with all of that information. Yes.